Hi class, welcome to Chemistry Made Easy. Do you have difficulties when it comes to the study of the mass spectrometer operations and its calculations? If yes, today I'm going to take you through the operation of the mass spectrometer and the various calculations it comes with. So let's move on to look at that topic. So today we'll be looking at the mass spectrometer. When we talk about the mass spectrometer, how does it operate? So let's look at the diagram involving the mass spectrometer. So this is a sketch of our mass spectrometer. So basically, the mass spectrometer has these are the entry points of our sample. So that's the entry point of our sample we want to identify. And this region is known as the vaporization chamber. This is our electron beam, normally produced by an electron gun. This region gives us what we call the acceleration chamber. We have a detector. We have a magnetic field. We have a monitor. So how does the mass spectrometer work? So we're saying that if you want to know how the mass spectrometer works, the first thing you need to do is you take your sample that you want to identify, mostly an isotopic sample, okay? So you take that isotopic sample, you pass it through these entry points. When the sample gets to this entry point, the first compartment it gets into is what we call the vaporization chamber. In the vaporization chamber, it contains what we call a heated filament. This heated filament is going to burn our sample into a form of vapor. Okay, so when that vaporized sample is being produced, the next thing is that the next compartment is what we have where we have the electron gun. The electron gun is going to eject electrons onto our vaporized sample. Now, when these ejected electrons are exposed onto our vaporized sample, the electrons come into contact with the atoms or the molecules of the vapor. And when that happens, you realize that the molecules or the atoms will lose some electrons. And when atom loses electrons, they form what we call cations. So these cations are now going to travel through this medium, which is our next compartment known as the acceleration chamber. They are going to enter into a variable electric and magnetic field. And then the sample is then going to be deflected based on their mass to charge ratio, based on how heavy or how lighter the samples are. So lighter samples will be deflected more and heavier samples will be deflected less. These samples will then be detected using the detector. And then this detector is going to identify this sample, or is going to eject this sample onto a monitor, or to be projected on a screen where you see the various isotopes in the form of a spectrum. So basically, the mass spectrometer in this regard is used to determine the relative atomic mass and the relative molecular masses of isotopes. But we have various spectrometers. We have spectrometers that can be used to identify the level of pollution in an environment. In our next lesson, we'll be looking at how to calculate for the relative atomic masses or the relative molecular masses of sample. Before we look at how to calculate for the relative atomic mass or the relative molecular masses of substances, there's one thing you need to note. When samples are passed through the mass spectrometer and you end up having only one spectrum, then it indicates that that particular sample is not an isotopic material or an isotopic sample. Okay, so when you have one spectrum or zero spectrums, it denotes that that is not an isotopic sample. But if you have more than one, like two or upwards, then it indicates that that particular spectrum or that particular sample is an isotopic material. So let's get into today's lesson. We want to look at how to calculate for the relative atomic mass or the relative molecular masses of samples. How do we do that? It's simple. Now, to calculate for, or let's say, calculations involving the mass spectrometer. To do calculations involving the mass spectrometer, we need to use this formula. So I have AR of X, which indicates the relative atomic mass of my sample. I don't know what sample it is. I am assuming that that sample is X. So that sample is equal to the summation of the isotopic or my atomic mass, okay, times the relative abundance. All these over my total abundance. So my relative abundance can be either percentage abundance or fractional abundance. Also note that when we talk about percentage abundance, it should sum up to 100%. Whilst we talk about fractional abundance, it should sum up to 1. So take note of that. Now we're going to take questions and see how we can apply this formula in calculations. Now, before we do that, there are various ways that we can calculate for our relative atomic mass. In questions, there are questions whereby you will be asked, where you'll be provided with the isotopic mass, but yet you will not be given an atomic mass. In that question, then the isotopic mass can become your atomic mass. But in a question where you have both atomic mass and isotopic mass, then you use the atomic mass in your calculations. So you take note of that. We are going to take series of examples where we will have one given, or one of the examples where we have only isotopic mass, yet we don't have atomic mass. In another example where we have both isotopic mass and atomic mass. Then in the other examples, we will be asked to calculate for the relative abundance of the various isotopes. So we'll see how we go about that. So let's take some examples. In our first example, the question reads, naturally occurring chlorine is 75.78% chlorine 35 with an atomic mass of 34.969 AME and 24.22% chlorine 37 with an atomic mass of 36.966 AME. Calculate the relative atomic mass of chlorine. Now, in this question, you could see that we have been given both the atomic mass and the isotopic mass. So where we have both atomic mass and isotopic mass given, we have to use only the atomic mass for our calculations. So let's go ahead and solve that question. So solution. So in the question, we quote our formula. The relative atomic mass, this time not of X. We know what X is. In this case, X is chlorine, is equal to our summation. The summation of what? Our isotopic or our atomic mass times our relative abundance. All these over our total abundance. So we're given both the atomic and the isotopic mass. We are going to use the atomic mass. So for chlorine 35, they said the atomic mass was 36.969. 36.969 AMU. For chlorine 37, they said the atomic mass was 36.966. 36.966 AMU. So, and each percentage abundance for this was 75.78%. This one was 24.22%. So we are going to substitute this into our formula. We'll have our relative atomic mass of our chlorine to be equal to the summation of 36.969 times 75.78. Please don't always bring the percentage sign because we are going to divide by the total abundance. Okay, so plus 36.966 times 24.22. All this divided by 100 yet, but we have to show how we got 100. So I have 75.878 plus 24.22. So my relative atomic mass of chlorine, when done properly, is going to be 3,550 over 100, which gives me 35.5. That is the relative atomic mass of chlorine. So this is a question where we know both isotopic mass and atomic mass. In our example 2, we are going to look at how to calculate for the relative atomic mass of an element or an isotope when we are given only the isotopic mass but not an atomic mass. Let's take the example. There are two isotopes of chlorine, chlorine 35 and chlorine 37. The percentage abundance are 75% and 25% respectively. Calculate the relative atomic mass of chlorine. In this example, you could see that chlorine, we were only given the isotopic mass, not an atomic mass. So solution. Our relative atomic mass of our chlorine is equal to the summation of our isotopic or our atomic mass times our relative abundance. All these divided by our total abundance. So what do we know in the question? In the question, we're given the isotopic mass, which is chlorine 35. They said it was 75%. Chlorine 37 was 25%. So here we are going to substitute our isotopic mass as our atomic mass. So I have AR of my chlorine, which is my relative atomic mass of chlorine, is equal to my 35 times 75 plus my 37 times 27. All this divided by the total abundance, which is 75 plus 25. 25. I'm going to get 3550 divided by 100, which will give me a relative atomic mass of chlorine as 35.5. So this is how we calculate for isotopes that have only isotopic masses and not an atomic mass. Now let's go and look at an example where we've been asked in the question to find the relative abundance. It could either be fractional abundance or percentage abundance. How do we go about that? So let's take an example and see how to calculate for the relative abundance of the various isotopes. In our third example, we are going to look at how to calculate for the percentage or the fractional abundance of the various isotopes in a sample. So let's take an example. Naturally occurring boron consists of two isotopes, which is boron 10 has an atomic mass of 10 AMU. Boron 11 has an atomic mass of 11 AMU. The relative atomic mass of boron is 10.8. Calculate the percentage abundance of the various isotopes of boron. So this is a question where we are no longer looking for the relative atomic mass because it was given to us in the question. So we are calculating for the percentage abundance of the various isotopes of boron. So let's solve that. So we know that in our question, we're given the relative atomic mass of boron. They said it was 10.8. Now, the various isotopes of boron are boron 10 and boron 11. For boron 10, they said its atomic mass was 10 AMU. For boron 11, it was 11 AMU. So, we are looking for the percentage abundance of boron, which we don't know. But we know that our relative atomic mass of boron is equal to the summation of either our isotopic or our atomic mass times our relative abundance. All these divided by our total abundance. So, we are looking for the individual isotopes of boron, the percentage abundance. So, if this sample was supposed to be passed through a mass spectrometer, the first sample that would be given out is the boron 10, where it has the what? The lighter mass. Okay, so that will be the one that will be ejected or it will come out first. So now we are going to take that. Our boron 10, since that's going to be the first sample that will be identified or to come out from our mass spectrometer, we will assume that that is an X%. So if you don't know the percentage abundance. The next example is boron 11. So if we are able to get boron 10, which is X%, to get boron 11 is going to be what? We are subtracting the total percentage is 100. So we're going to get 100 minus X%. That's boron 11. So we're going to substitute these informations onto our formula. For the relative atomic mass of boron, we said it is what? 10.8. Our isotopic mass in this, or our atomic mass for boron 10 is 10. What's this relative abundance? Is X plus, the next is boron 11. Its really atomic mass is 11. Its percentage abundance is 100 minus X. Divide all these by the total abundance, which is what? 100. So we are going to get 10.8 is equal to 10 times x will give me 10x plus 11 times 100. I'm going to get 1100 minus 11x. All these divided by 100. I'm going to multiply 2 by the denominator. I'm going to get 100 times 10.8 is equal to 100 times 10x plus 110 minus 11x all over 100. This can cancel. 100 times 10.8 will give me 1080. This will give me 10x plus 110 minus 11x. I'm going to group like x, so I'm going to bring this one here. I have 11x minus 10x is equal to 1100 minus 10, 1080. This will give me x. This is going to give me, when I subtract this from this, I'm going to get 20. So x in this case is 20. Okay. So I can now say therefore, okay, for boron 10, I said it was x percent. So boron 10 would be equal to 20%. For boron 11, I said it was 100 minus x percent. So it's going to give me 100 minus 20%, which will give me 80%. So our percentage abundance of boron, which has a relative atomic mass of 10.8, is going to be 20% for boron 10 and 80% for boron 11. So this is how we calculate for the relative atomic masses of boron. I hope you understand. If you had a nice lesson, I urge you to subscribe to Chemistry Made Easy so that you will not miss out on all our lessons. Thank you.